This paper is about the coherence of an atomic Josephson junction in the presence of external noise. The dynamics of a Bose-Einstein condensate of many atoms in a double well potential is equivalent to a Josephson junction of two superconductors with a tunneling barrier between them. The system can be thought of as an ensemble of many two-level systems represented by the Bloch sphere. A state where most of the atoms are in the right well is represented by a distribution near the south pole, while a state where most of the atoms are in the left well is represented by a distribution near the north pole. The ground state is usually a state where the population of the two wells is equal and represented by a distribution near the equator. If the atoms are not interacting, then the ground state is a coherent state, where each atom is in a superposition of the two wells equally. However, in the presence of repulsive interactions, the ground state is a partially localized state, where some of the atoms are mainly in one well and some of the atoms are mainly in the other. This means that a phase difference applied between the wells will cause less transfer of population between the wells than in the case of a non-interacting system. The Bloch sphere near the equator can be reduced into a flat phase number space. In the phase number plane, this looks like a number squeezed state where the phase distribution is stretched and the number distribution is squeezed by a factor psi. What happens when an external noise induces phase difference fluctuations between the two wells? We describe the evolution as a random walk process of phase jumps combined with Hamiltonian evolution in the double well trap. The different colors in the wells represent difference in phase between the wells. The phase jump is followed by a Josephson oscillation dynamics where the phase difference transforms into number difference, but the number difference is much smaller than the number difference in a non-interacting system due to this number squeezing effect. The rate of loss of coherence is proportional to the rate of growth of the sum of squares of the number fluctuations and the phase fluctuations, so that in the case of number squeezing, the rate of loss of coherence is suppressed by suppressed number fluctuations relative to the non-interacting case, represented by the dashed circle. What happens when atoms are lost from the trap? In a non-interacting system, each atom that is lost from one trap is also lost from the other trap equally. But in the case of interactions, the loss of atoms from the traps creates number fluctuations. These number fluctuations are translated into phase fluctuations, but in this time, due to the squeezing effect, the phase fluctuations created by the number fluctuations are much larger than in the case of a non-interacting system. This means that loss can induce decoherence and enhanced decoherence in the system. In this paper, we discussed the effect of external noise and its interplay with the interactions between the atoms on the decoherence of Bose-Einstein condensate in a double well, especially in the context of magnetic fluctuations very close to an atom chip.